Hi, my name is Megan, and I'm here with Kennedy, Hallie, and Mia, and we are going to discuss the water in Libya. We decided to study Libya and find ways in which we can improve their clean water sources and access in the future. Libya is located in the Maghreb region of North Africa, with the majority of the country located in the Saharan Desert. The majority of Libya's population is located along the northern coast, especially in the three largest cities of Tripoli, which is the capital, Benghazi, and Misrata. The country's population is about 6.9 million people, and the official language is Arabic. The country also has a GDP of 25.4 billion US dollars. I'm now going to pass it off to Hallie to discuss the politics in Libya.
Thanks, Megan. So the politics in Libya have been a bit complicated over the past several years. They've recently ended the second civil war that lasted from 2014 until 2020. There have been conflicts with who is actually running the country. The socialist leader, Gaddafi, has dominated the political climate in Libya for decades, and he was killed in the first civil war, with now leading the current leader, who is now Fayez al-Sarraj. Gaddafi instituted a government made of a pyramid shape. This allows the participation of the citizens of Libya. I'm now going to pass it off to Kennedy to introduce Tamasa.
Tamasa is a small town in the Sahara Desert of central Libya, about 300 miles from the Gulf of Sidra. As it is in the desert with high temperatures and low precipitation, Tamasa is a great candidate for water improvement initiatives. It lies about 100 miles southeast of Saba, another larger town in Libya, and Tamasa is about 500 people. It's a small town. They have a gas station and a mosque in the town as well. And here you can see this map to give some context of the geography of our presentation. Some countries that border Libya include Egypt, Sudan, Chad, Algeria, and Tunisia. And here you can see Tamasa indicated here by this red mark. You can see it's far from the coast, not near the Mediterranean Sea, or the larger cities of Tripoli or Benghazi. Now I'm going to pass it off to Megan to talk about the weather in Tamasa.
Thanks, Kennedy. As shown on the slide, you can see the average day and night temperatures in Tamasa throughout the year. The humidity tends to stay between 17 and 43% throughout the year, which makes sense since Tamasa is located in the middle of the Saharan Desert. The daytime temperatures range from about 18 degrees Celsius on average to 38 degrees Celsius, which is equivalent to 64 degrees Fahrenheit to 100 degrees Fahrenheit. There are about 19 days of rain a year in Tamasa, which is not very many. And this partially explains why we chose Tamasa to focus on our project in order to find better methods for water to get to the village. And we think it's really important to find more ways for clean water access for the people of Tamasa. I'm now going to pass it off to Mia to talk about the aquifer.
Thank you, Megan. In 1953, efforts to find oil in southern Libya led to the discovery of large quantities of potable fossil water underground. This led to the Great Man-Made River Project being conceived in the late 1960s, and work on the project began in 1984. The project's construction was divided into 5 major phases. The Great Man-Made River is a network of pipes that supplies fresh water from the Nubian sandstone aquifer system across Libya. The Nubian sandstone aquifer system is the world's largest known fossil water aquifer system. It accumulated during the last ice age and is not currently being replenished. The water covers a distance of up to 1,600 kilometers and provides 70% of all fresh water used in Libya. Next, here's a map of the Great Man-Made River, which shows a network of pipes located throughout Libya. Now we'll talk about issues with the water in Libya. So despite the Man-Made River Project being one of the largest civil engineering constructions in the world, the pipeline provides water that is considered unfit for drinking. Inadequate chemical treatment and equipment shortages have damaged water quantity and quality. Unsafe drinking water increases Libya's risk of waterborne illness. In July 2019, UNICEF spokesman for Libya, Mostafa Omar, estimated that nearly 4 million people out of Libya's 7 million people would not have access to safe water in the event of a pipeline disruption. Diseases like cholera, hepatitis A, and diarrhea may spread as a result of this lack of sanitation in Libya. The generalized lack of attention by state officials to the importance of water issues in general has left people to dig aquifers in their houses without any supervision or legal permission. Lastly, independent estimates indicate that the aquifer could be depleted of water in as soon as 60 to 100 years. Next, I'll pass it off to Kennedy to talk about our possible solutions.
Thanks, Mia. Yes, so as Mia previously mentioned, the water in the aquifer near Tomasa is not clean water. Pollutants in surface water can filter into the ground and enter the groundwater aquifer. Irrigation water can bring in pesticides and other chemicals. Water can seep through landfills. Tanks of gasoline stored underground can leak. So basically, as you can see, there are many circumstances that risk the cleanliness of groundwater in aquifers. However, for the most part, aquifers do actually do a good job of cleaning water naturally as water passes through small pores, which naturally remove substances. However, because the water is not completely clean, we will use chemicals in order to treat the water and clean it through a process called remediation. This pump and treat method is a common one for cleaning up groundwater that's been contaminated with dissolved chemicals, including industrial solvents, metals, and fuel oil. This is the cheapest and easiest way to treat water in the aquifer. And this is a process when a barrier is constructed within the aquifer, and this isolates the contaminated groundwater from the rest of the aquifer, where the contaminated groundwater can then be treated. So there are two ways that this process can occur. Bioremediation is one way to treat the water through the use of microorganisms to consume the remaining bacteria in the groundwater. So basically, these microorganisms are bioengineered to eat the pollutant that is in the water. And so these organisms are injected into the contaminated region, and they then consume the pollutant, which cleans the groundwater in the aquifer. And then the second way is chemical remediation. This can also treat the water in the aquifer. A chemical is pumped into the aquifer, and that chemical then destroys the contaminant. So once we complete these steps, we'll be able to drill clean water out of the ground using a prototype that we'll talk about in the next slide. But one more note, it is more expensive and difficult to drill the water and then treat it. So that's why we'll be doing so before removing it in the ground when it's in the aquifer. So now I'll explain our proposed method to get more clean water to the Tomasa community, and that's by drilling wells from nearby aquifers. And as you can see here in this sketch, the drill is made up of multiple parts that effectively extract water. So you can see there's a control valve, which regulates the flow of liquid or gas by opening or closing the internal passages. There's a hydraulic power source, which acts as a motor powered by hydraulic pressure. And the hydraulic rotary and swivel is required here, and that prevents cross-contamination or leakage. And then the mud pump is used to circulate drilling fluid downhole during the drilling operations. And so there are many features that make this drill great for getting more water to the community. So the drill can reach 300 feet below ground level and can bypass through various types of surfaces like sand or hard rock. Another feature is the optional tri-cone roller bits and drill collars that adapt the drill to these various conditions. It also includes a 3,000 PSI pump system, and the unit's bypass flow control provides 5,000 pounds of powerful force, ensuring the drill reaches its desired depth. So in this next slide, you can see a sketch that outlines how the hydraulic drill works and how it will benefit the community by increasing access to quality water and allow for it to be distributed throughout the town. So you can see the drill going through the layers of rock and sand, being able to get more water from the local aquifer. So now I'll be passing it off to Megan, who will explain the water wheel, which is a means of efficient distribution of clean water to the Tomasa community.
Thanks, Kennedy. In tandem with creating more clean water, we have proposed a way to distribute it through our idea of the water wheel. This allows for large quantities of water to be easily transported by women back to their respective villages and communities. In the past, women have had to carry water nearly a mile several times a day in order to get it back to their village. These water jugs could weigh as much as 50 to 60 pounds. It is much less draining and more effective than the alternative of carrying water jugs on their heads. And here is a sketch of what the water wheel looks like.
Finally, we wanted to take a look at the pricing options for the solutions previously mentioned. The drill has a price range about $10,000 to $50,000 each. This range is dependent on how many specific features each drill has. Also, higher end drills tend to be on the higher end of this price range. Finally, with the water wheel, the water wheel has a price range about $20 to $50. A 25 to 30 liter container has a price range about $20 to $30, while larger containers will have higher prices, which will be about $50. Thank you so much for listening.